Well, greetings out there in YouTube land, and welcome to today's video, which is entitled Isolation Transformers. In response to viewer demands, I'm preparing a video series on how to operate an oscilloscope, primarily to troubleshoot audio amplifiers. And while preparing for that series, it occurred to me there are several collateral issues that had to be resolved before we could really move on to understand how to safely operate our oscilloscope, and primary amongst those was the isolation transformer issue. Now, to fully understand the problem, I think we need to go back more or less to the beginning and gain knowledge along the way so that finally we'll be able to understand the need and benefit of isolation transformers. I think most of us know that the reason alternating current won out over direct current is that it can be stepped up to very high voltages for transmission through miles of power lines with very little loss compared to DC, and then stepped down by transformers on site in different neighborhoods to levels of voltage that are appropriate for household use. My example, I start off with 35,000 volts AC being applied to the primary of the step-down transformer. These transformers are quite large, they're tubular, and they're oil-filled so that the core is cooled by convection currents through the oil. The secondary consists of 3 wires that exit from the transformer. There is a center tap return wire, and then 2 hot wires. Each has 120 volts AC potential to the center tap return wire. The center tap is grounded by using a heavy gauge wire that runs down the pole and all the way to the tip of the pole that is buried deep in the ground to provide a good earth ground for the center tap. Why do we center tap it? Well, think about why we center tap the 6.3 volt filament winding in our amplifier power supplies. By giving a ground reference to this center tap, we ensure that the voltage is equally divided between the 2 output wires and that voltage remains consistent. Also, because of the center tap, the 2 120 volt AC wires that come from the winding are out of phase. Each of the 120 volt AC wires is used to energize half of the wall receptacles in your house. That means that half of your house will have receptacles energized by this wire, the other half will be energized by this wire, and that means that half of your sockets are out of phase with the other half. However, this is not an issue. This is not an amplifier circuit, so for household use, the out of phase condition.
Okay, here's the step-down transformer that's out behind my house, and you can see the big heavy ground wire coming down the pole and going all the way down to the base tip of the pole that is buried deep in the ground. So that is the grounded center tap of the secondary of the step-down transformer. Okay, here's a close-up of the power lines coming to the house, the 2 insulated 120s and the bare uninsulated common return.
Our wall receptacles are wired with the smaller of the 2 slots receiving the hot wire, the wider of the slots receiving the center tap return wire, and then a circular ground receptacle at the bottom that we will plug our 3-wire plug into, that not only is earth grounded but also connected to the center tap return. This is for safety purposes. This gives 2 routes for the electricity to return. If electricity shows up on this ground lug, it shouldn't, but if it does, it can pass through the ground back here to the center tap, or it can pass through the return wire to the center tap. So it's, like I said, for safety reasons, it's like a double provision here of return capability in case of a short circuit. Now let's look at the 3-wire power cord plug that we're going to plug into the receptacle. Right here is the narrower of the 2 prongs, which will go into the narrow slot, and the hot wire here will be connected to the hot wire here, which is generally the black wire in a 3-wire power cord. That wire will continue on through a fuse, an on-off switch, and go to the primary winding of our power transformer. The wider prong will plug in here to the wider slot, which is our return wire, our center tap return wire, and it will proceed down here to also to the primary of the power transformer. Now I've indicated an earth ground for that wire, and I've done it with dotted lines because as it stands, just as you see it, this is not true. But the moment that you plug this plug into this receptacle, remember that the white return wire is wired not only to the ground slot, but also directly to an earth ground. Before I go any further, I wanted to clarify something that might be confusing to some of you, and that's the symbol that I'm using here for earth ground. Now, most of us are familiar with the symbol that looks like an upside down Christmas tree, which indicates a chassis ground that we see all the time in our amplifier circuits. But I'm using this symbol to indicate something completely different. Now we know with the chassis ground that indicates that the wire goes to the chassis and that electricity will pass through the chassis to get to wherever it's trying to go, maybe to its origin at a transformer winding or something like that. But this indicates that the earth itself could serve as a chassis, if you will, and that electricity can pass through the earth itself to get back to, say, the center tap of that transformer up at the top of the pole in my backyard. So 2 very different things. This is a metal chassis that we would have in an amplifier. This would indicate almost like an earth chassis through which electricity can pass. Now I'm going to tell you a little story here which is going to, I hope, stick with you, and keep in mind a phenomenon about the route that electrons take in a circuit. Years ago when I was a kid, I used to go horseback riding in the desert. Now there were 3 different stables spread out over about a quarter-mile area, and you could rent your horse from any of those 3. And on any weekend there might be 100 people riding horses from all the 3 different stables out in the desert, everywhere, up mountains, down arroyos, all over the desert, completely mixed up. But the minute that you turn those horses around and they knew that they were headed home to go get food and water, they would take off like bats out of hell and take the straightest route possible back to their own stable. Now there was food and water at all 3 stables, but the horses only returned to the stable from which they had come originally. Now with that analogy, I'm going to explain to you why the primary circuit in an amp is the most dangerous part of the whole amplifier circuit, and why the secondary circuit is not. Okay, in the primary circuit, we can say that it is not only ground referenced, but earth ground referenced. Earth ground reference means that when the horses decide to head back to the stable, okay, they're out here riding through the coil, and they can head back to the stable, they can take a shortcut through earth ground, if need be, to get there. Now, here is how that can happen. You are standing on a cement floor, ankle deep in water, barefoot, and you reach in here and touch with one finger any part of bare wire that's present in the primary circuit, and you are toast, okay? You're fried. And here's why. Because those horses are galloping around here, and they say, hey, look, this idiot who's standing in water, which will connect to the ground, the earth ground, is touching the circuit. The heck with going all the way back this way. Let's just cut back through the ground and get back here to the center tap, where there's plenty of food and water. Now, why is the secondary circuit not as worrisome as the primary? The horses over here are leaving the stable, going out here and galloping all around through the circuit, doing whatever it is that electron horses do, and they will return only back to this winding. The horses from this stable will only return here, and likewise right here. If you were to stick your finger in here and touch an open spot in the wiring, the horses would run right by you, because you cannot give them a shortcut to ground, because this side of the circuit is not ground referenced. They cannot take the shortcut to earth in the secondary side of the circuit like they can in the primary. This is not earth ground referenced. Now, I'm not telling you to stick your finger in and find out, because due to the fact that human beings are big bags of water that have a fairly high amount of capacitance, if you touch in here and touch a live wire, the electricity is going to charge you up. It's not going to form a circuit between you and ground, but it's going to charge you up, okay? And while it's doing that, it is passing through the nerves, say, of your fingertip, and it is hurting like the devil, okay? So it's still painful, but because a circuit between this and earth cannot be formed, you are not really at risk of any sort of a fatal shock unless you commit the unmentionable, and that is to touch with one finger a location that has high potential, and with the other finger, on the other hand, touch an area of low potential. Then the horses can gallop through you. They're not using ground to get back to the center tap. They're using your body to get back to the stable quickly by taking a shortcut. So that's why we tell you to keep one hand in your pocket when you're touching anything, any circuit in an amp. So you cannot close a circuit. Even in the secondary, you can't, if you only have one hand in use here, can't close a circuit that could lead to your demise. Look who decided to join us here on the table during the discussion. But as the master of concealment, you wouldn't know he's there because he's under the tablecloth. Excellent work, Jack. Excellent. No one would ever suspect you're under the tablecloth. And now he'll probably fall asleep and we'll hear him snoring in just a minute or two. Now, what if we could magically change this somewhat dangerous primary side of the circuit and eliminate this earth grounding that it has here? If we could eliminate that, then both sides would be as safe as the secondary side is already. And the way that we can do this is with an isolation transformer. Okay, here is our isolation transformer. It's generally a 1-to-1 winding ratio because we don't want to step up the voltage or step it down. We want it 120 volts AC on both sides. We have a standard 3-wire plug for the primary side. We will plug it in, and we can even use a chassis ground if we want on our third grounding lug here. And say this is in a metal box, we could ground the metal box for safety, which would be a good idea. We also see that this primary is earth ground referenced, because the common ground wire is plugged in to a receptacle where the common wire has both earth ground connections and chassis ground connections. So this side is still very much like the primary that we're trying to get away from in our amplifier circuit. But the secondary is very different. Because there is no connection here, no direct connections between this winding and this, there is no earth ground reference on this side of the transformer. This is very much like the secondary was in our amplifier. You see that the earth ground referencing is limited to the left side of the transformer and not over here. These horses, once they leave the transformer, don't want to go to ground. They don't want to go anywhere except back on this return line to the stable. And that's all they're going to do. So we have eliminated the possibility of touching with one finger anything in here while we're grounded and being killed. So now let's plug our amplifier into the secondary of our isolation transformer. When we do, we see that there is no earth ground reference on the common wire that we saw before when we plugged into the regular AC wall receptacle, and therefore the horses in this circuit cannot pass through us and take a short circuit back to the center tap at the top of our pole in the backyard. That makes this much safer. Now the primary of our amplifier circuit is just as safe as the secondary was in the original circuit. They're both isolated from ground reference, and the horses that are galloping around in each of these circuits cannot possibly take any short circuit back to the corral through us if we are grounded. This is why people recommend the use of isolation transformers with amplifiers that do not have power transformers. If you think about it, if you take away the entire power transformer, all you have is AC winding through all of the circuitry of the amp. And what are the odds that there may be leakage to the chassis somewhere along that route? And if you touch that chassis and you're grounded, what are the odds that you're going to be electrocuted? In both cases, the odds are pretty good. Once you plug a what we call series filament or power transformerless amp circuit into an isolation transformer, yes, all of the AC is marching all through the circuit the way it always was before. But because no part of the circuit has earth ground referencing, none of the horses galloping around here in the circuit can possibly take a shortcut through you to ground and back through the earth to that transformer on top of the pole in your backyard. So using the isolation transformer will render then one of these rather unsafe circuits without a power transformer into a relatively safe device that you can operate without undue concern for being fried sometime during your concert at Wembley Stadium. But why, you may ask, do we need an isolation transformer when we're working with an oscilloscope? Well, first off, you don't need it for the oscilloscope itself. You need it for the device that you are checking or testing with the oscilloscope. To see the benefit of using an isolation transformer on, say, an amplifier that we're going to check with an oscilloscope, let's use our oscilloscope here on the amplifier circuit that is plugged into a regular wall receptacle. Now let's look at how it's made first. Here, the probe. The probe's got a plastic body with a little metal wire that runs down the middle with a hook that you can hook onto different points in the circuit of the device that you're checking. There is a adjustable 1 to 10 million ohm resistor in series with that wire. You can set it for times 1, in which it will be 1 meg ohm, or times 10, in which it will be 10 meg ohm. The reason for that we'll explain when we get into oscilloscopes, but for now, the point is there is a whole lot of resistance right here that will prevent, in the case that we touch this to a high voltage spot, the voltage will come raging down here. And can you imagine the voltage drop across 10 million ohms? This then is the buffer that pretty well protects us from harming our oscilloscope by touching the lead here to a high voltage spot. You still have to be careful, but this resistance actually then reduces the chances of harming the instrument. We see that that hot wire comes in here and goes into the circuitry of the oscilloscope. Now there is a shielded cable on the outside that connects to the body or the chassis of the oscilloscope. Also, when we plug in the oscilloscope, we know darn well that the ground lug will come over here and connect to the chassis, and that the ground lug and the return are both earth grounded. Therefore, the chassis of our oscilloscope is referenced to earth ground. Now, I think that by now you should be knowing that that's a hazardous situation, because with that oscilloscope test lead, there's two connections. You know, anytime you want to test something, you have to make two connections. Well, we've got that one there at the tip. That's our main connection. Then we've got our ground clip. This will be connected to the shield of our test probe, and it looks like a little alligator clip. And we can clip it around in here to different places in our amplifier to see what waveform the signal is taking. We can measure voltage. You can do all sorts of measurements, but you need to connect the ground clip somewhere. Well, since the oscilloscope is ground referenced, if you hook the ground clip up to anything up here in the AC circuit, or that's exposed to the AC circuit, or inadvertently connected to it, or that is being leaked to by the AC circuit, you're going to have a dead short between the ground clip and earth ground, and all sorts of current is going to start flowing through here very rapidly, because remember, it's coming down the ground clip, down the shield, around the chassis, and going straight to ground. You have an absolutely dead short for whatever voltage or current you've connected this to. Now that will rapidly destroy the probe, and sometimes in very exciting ways, okay, with sparks and melting plastic and smoke and burning your hand and causing all sorts of things that will kind of ruin your day. Now let's use the oscilloscope on the same amplifier, but in this case let's plug it in to the isolation transformer. Now, while the amp is plugged in, the horses are running in this type of a pattern. They're originating over here, they're running over here through the power transformer, and then they're coming back, and this is their stable. That's the only place they want to go. If you hook this little ground clip in here somewhere, the horses will not even notice it. They'll be running back because they want to get over here to the stable. They have no interest in running down this wire along the shield through the oscilloscope chassis and going down into the ground and trying to get back to the center tap at the pole, because they didn't originate there. The horses now in our amplifier circuit and the secondary of our isolation transformer originated right here. They have no desire to go anywhere other than in this circuit. Therefore, our oscilloscope leads are safe, because nothing can entice the electrons to take this route and cause any damage. And while we're talking about oscilloscope leads, I'll just show you one here so you can see how it relates to the drawing. There's a little hook that comes out that we can use to hook on to different wires and locations in the amp circuit we're studying. Here is that ground lead that can cause so much trouble if the device that we're working on is not plugged into an isolation transformer. Here's the little switch. You'll see there it's a 1 meg ohm resistance to the signal, and we move down here and it's 10 meg ohm resistance. Okay, and not much else but shielded cable coming out here to a connector that attaches to the oscilloscope so that the shield's on the outside and the signal passes down the little wire in the middle. And we've got this mysterious screw on top, and you're going to have to wait a little while to find out what that's all about if you don't already know. Let's take a few moments here and let me open a gift that I received through the mail just today from a very generous and thoughtful viewer. I just had to share this with you. A viewer sent me an amp chassis. We'll take a look at it in just a minute, but I thought you'd get a kick out of the address. And I guess that's Jack there, looking a little dog-like, but not bad. Oh, this is a warning, pretty ominous. I think you'll get a kick out of my padding that I used, but it depends on how you look at it. I guess we know what it's going to be. Let's open it up and see. Yep, sure enough, a nice Depends thrown in here for padding, and thank God, because I'd almost run out of them. Okay, this is cute. The tubes are stuck into foam rubber, and the amp chassis is all wrapped up in some kind of, oh no, it looks like a diaper or something. Let me remove that and we'll see what it looks like. Yep, it was wrapped up in an adult diaper. Thank heavens it's a fresh one, not a used one. But anyway, here is the amp chassis. It's an Airline from Montgomery Ward's. 6AU6, 6V6, 6X5 rectifier. Nice power transformer. Looks all original underneath. So I've got to find a good project to use this in. Thanks, Ed. I really appreciate it. Well, that about does it for this video on a rather complex topic. We started at the top of a 40-foot pole in my backyard and ended up here at the kitchen table looking at oscilloscope probes. I hope you enjoyed the journey, and I hope it was helpful and instructive. I want to offer my sincere thanks to all the Patreon people who make pledges and the PayPal contributors. You're keeping us on the air and advertising free, and I think we all benefit from that. So thanks so much to all of you for watching, and I hope to see you in our next video, in which we will start to understand and operate a oscilloscope and use it to troubleshoot amplifier circuits. If that sounds interesting, stay tuned. Looks like we've got a 31 Ford Coupe. You can tell the 31 when the area here in the grill contrasts with the chrome Ford engine that's set way back. When you set back a Chevy engine like this, the distributor is way at the rear and impossible to get to or to remove. But the beauty of a Ford engine is the distributor's up at the front. Look at those headers, powder coated. Look at the craftsmanship. Having tried to build some of these things, I can tell you, this isn't easy. These guys are good. Beautiful car.
Oh, that's all fiberglass.
You're from New Mexico?
Yes, sir.
Yeah, we're in Chapter.
Oh, okay.
Absolutely gorgeous car. Even has the flat headlight lenses like the originals. Probably with halogen bulbs behind them. And now in the what hath God wrought category, is it black 40 Willis, the blown big block Chevrolet. This is a fiberglass replica, but who cares? I
think I'd give you my life savings just for one ride. Really something. Very subtle. If you're a 33 and 34 Ford fan, this one might work for you. 3-window coupe, gorgeous wheels, knockoffs, small block Chevy. Super nice. This car belongs to the host of the get-together today. It's probably the nicest T-bucket I've ever laid eyes on. I don't think I changed a thing about this. The wheels, tires, certainly not the engine. I've asked him, what's it like when, say, you out on the road and you don't see any cops around and you really stand on the accelerator, and he just looked at me with that look like guys that come back from war, that 100-yard look or whatever it is, like you don't want to know. And I believe it. Can you imagine? Probably 700 or 800 horsepower and about a 1,500-pound car. Ugh. Okay, here we got a 1925 Model T, what they would call a tall T pickup truck. And look at the starter crank is still in position. Got the old-fashioned headlights with the brass rims. Original grill shell. You start to get suspicious when they see the rack and pinion steering protruding out in the front. Start to think, well, maybe it's really not a Model T. Look at those running boards. Old Henry never dreamed up anything like that. Neat rear wheels. He's got the little lanterns. Got the brass fire extinguisher. And I'm going to guess that those are the rear turn signals. If they are, I got to hand it to him. And I'm sure the police will be handing it to him too, in the form of a ticket. Lantern tail lights. Very, very nicely done. Look at that bad diamond plate toolbox. Nice choice of tires and wheels. Overall, I don't think I've ever seen another car quite like this. I think it's really original and really neat.